Hello everyone. Let us look at the properties of linear system. So up till now we have looked at what are the system, how does the linear system looks like. So essentially we have a system which looks like this: x prime of, let's write down as the variable as t, which is at x of t plus b of t. Okay, yeah. And here we are assuming that here A of t is a n cross n matrix, right? Is a n cross n matrix with entries aij. Clear? And these aij, of course, they depend on x. So let me put it this way: they depend on x. And bx here, okay, sorry, not x, because we are writing the variable as t, so this should be t, and b of t, okay, is a n cross 1 matrix, okay, and x of t, that will be your n cross 1 unknown vector, okay, is the n cross 1 unknown vector. Okay, so what are the components of x of t? X of t, the components should be xi of t, essentially, with components xi of t, xi of t. Okay, so let's just write it down properly and then that will make it more precise. So basically, for example, so for simplicity, we will just do it for n equals to 2. For simplicity, we will throughout this whole video, we will assume n equals to 2. I hope this is clear. Okay, exactly the same thing works for any n. So it does not really matter. Let's just do it for n equals to 2. That makes our life much easier. So essentially, for n equals to 2, how does it look like? It will look like this. You see, x prime of t, it will be a11 of t, right, x1 of t plus a12 of t, x2 of t. Clear? So a11, a12, these are the coefficients given coefficients, and x2 prime of t is a21 of t, x1 of t plus a22 of t, x2 of t. Clear? So this is the system given. Let's call this system as 1 for n equals to 2, and for a general m you can write it in a compact form, which looks like this. Here we are assuming here b of t is, generally speaking, it should look like b1 of t and b2 of t, but for our case, all purposes, we are just assuming this to be 0 for now. Okay, right. So this is a general form of a linear system, 2 cross 2 system. In this case, you can do it for n cross n. And what is the initial data? So generally speaking, the initial data which will be given to you in this kind of cases, so basically it will be called the initial value problem. Initial data will be capital X at the point t equals to 0, right? So x equals to 0 is, let's say, x naught. Okay, so this is a compact form. So what does that mean? It means that x1 at the point 0 and x2 at the point 0 will be given to you, and that will be x01, let's say, and x02, a vector in R2. Okay, right. So that's the problem. This is the one is the equation which is given to you, and the let's say initial data is this. So let's call this 2. So 1 plus 2 will be an initial value problem. Okay, initial value problem. So we'll call it a initial value problem for a system. Okay, right. Now there are some properties which this sort of linear system satisfies. What are those properties? So for now, I am not always going to write it as 1, but I am always going to write it as star. Okay, the system as star. Okay, so you see, the first thing is something called a principle. So this is very important, of superposition. Superposition. So see, we have seen that for a linear system, when we solve linear system, we showed that if y1 and y2 is a solution, c1 times y1 plus c2 times y2 is also a solution, right? So that is a superposition principle. So basically what this says is, let's say that let u of let x1 of t, let's just call it x1 of t, and capital X2 of t, so these are capital x1 of t, x2 of t, be two solutions of star. Okay, be two solutions of star. Okay, so I am starting out with this equation, start the first equation. So if they are the two solutions, now let's look at this. See what happens. X1 prime of t is nothing but a of t, x of t plus b of t, right? And so x1 of t plus b of t, and also x2 prime of t is nothing but a of t, x2 prime of t, x2 of t plus b of t. So those are always satisfied. Therefore, if we define a new function x of t, this is a new function which is nothing but c1 of x1 of t plus c2 of x2 of t. Now you see that x prime of t is nothing but c1 of x1 prime of t, which is nothing but a of t, x1 of t plus b of t, right? And plus c2 of x2 of t is nothing but at x2 of t plus bt. So at x2 of t plus bt, right? Bt. Now you see, this is an observation here that it implies that x2 prime is equals to c1 times, right? c1 times x1 of t plus c2 times x2 of t times at, right? Times at plus c1 plus c2 times bt, c1 plus c2 times bt. Okay, so you see, if bt is the zero vector, 0 in R2. Okay, so basically I am assuming that there is no bt, so it is a homogeneous equation. So that means that will implying that star is a homogeneous equation, right? Homogeneous system. Homogeneous system of equation. Then what does it say? That you see, x prime satisfies x of t, therefore x of t satisfies x prime of t equals to at times x of t. Okay, because c1x plus c2x, I defined it to be x of t. Okay, I defined it to be x of t. So this is definition. I should not write it like this. This is definition. Defined. Okay, so the x of t satisfies this. So you do realize that if you have two solutions, x1t and x2 of t, okay, and if you are dealing with a homogeneous system, this constant times x1, some c1 plus c2, c1 times x1 plus c2 times x2 also satisfies the equation, right? So that is always there, right? So now we come to we come to a very important property of something called a linearly independent set of functions. Okay, so definition. Okay, definition. Okay, so a vector valued function. So now we are talking about vector valued function. Okay, first of all, let's quickly recall what a vector valued function is. So essentially, we are looking for a function. We are basically saying phi is a vector valued function if phi, the domain of phi is R or a subset of R, and it takes it to Rn. Okay, so that sort of function we will call it a vector value. So basically, phi of t is a vector in Rn. You understand? So the value is taken in as a vector. So that's a vector valued function. So this is called a vector valued function. So you do realize here, whenever we are saying something is a solution, this is a vector valued function, this is the vector valued function. Okay, so you are dealing with vector valued functions here. Okay, so let's say the vector valued functions, vector valued valued functions. And what are the vector valued functions? Let's just call it x1 of t, x2 of t, xn of t. So I am working with like n sort of functions, okay, and they let's say they are defined on they have to be defined on a common interval, right? Defined on I, let's say some interval I, they are common interval, okay, are said to be linearly independent, linearly independent. So this is basically the same sort of idea what we do in vector spaces for general vectors also, but here for just for some sort of function. Okay, if c1 times x1 of t plus c2 times x2 of t plus cn times xn of t equals to 0 implies, as you know, for linearly independence we have c1 equals to c2 equals to cn has to be 0. Clear? And please remember the c1, c2, cn, these are all real numbers, right? And x1 of t, for fixed t, x1 of t has to be a vector, okay, in Rn. For n equals to, so if you are dealing with Rn, it is Rn, it is Rn. So basically what I am trying to say is this: if n equals to 2, it is basically a vector in R2. Yeah? Okay. So now when is it a linearly dependent? Of course, if one of the ci's are non-zero, then we have a linear dependence. So they are linearly dependent, dependent, okay, if okay, there exists constants ci's, okay. So basically let's say c1, c2, cn, okay, not all zero, so at least one non-zero, not all zero, such that this c1 times x1 of t plus c2 times x2 of t plus cn times xn of t, this should be 0. Clear? So very simple. Now let's look at some examples and then we'll proceed. So the first example which I'm going to give is this. So the most simple problems which you can think of is the functions which you can think of it as polynomials, right? Okay, so let's look at this thing. Let's look at this set 1, x square and x power n. Okay, so we are saying that this is linearly independent. This set is linearly independent. Okay, see, I am saying set is linearly independent. I mean, in most books they say the functions are linearly independent. Okay, that's what I mean here. Okay, so it means that the functions are linearly independent. I'm just doing it like this, but of course we should say it like this: the functions are linearly independent. Okay, linearly independent. Okay, I'm writing it like this just for avoiding any confusion. Clear? Okay, so these functions are linearly independent in every interval. Let's say every interval I, whatever the interval is, doesn't really matter, but they are linearly independent if they're defined, and is defined in whole of R. Okay, so how do you prove something like this? See, c1 plus c2 times x plus c3 times x square plus cn times x power n, this is 0, right? Okay, and if any ck is not 0, so let's say ck, there is a k which is not 0 for some k, okay, less than equals to n, for some k less than equals to n. Let's just assume that it is non-zero. So basically you see, if I have to show it is linearly independent, this should imply c1 equals to c2 equals to cn equals to 0. Okay, so if this is not the case, then at least one of the ck's has to be non-zero, and then the equation, you see, then this equation could hold for at least m-1 values of x, right? You understand? See, if one of the ck's are non-zero, so essentially what is happening is this, then this equation c1 plus c2x plus c m x power n equals to 0, this will hold for at most k values of x, right, of x. So basically what I'm trying to say is this. So there will be like k values of x for which they are like this relation should hold, right? Yeah. And then what happens is but the thing is, this relation in this case has to hold for all x, right? But it should hold for all x, should hold for all x, right? Okay, so that's a contradiction, and hence, okay, see, this is one way of looking at it. If you are not convinced, you can do it like this. Let's say okay, let me put it this way. Let's say 1 and x, are they linearly independent? How do you prove something like this? So please check this part. Check. Let's say this equation 1 and x, these two functions are linearly independent. How do you prove something like this? Linearly independent. Let me write it like this. How do you prove something like this? Okay, so you start with this c1 plus c2x equals to 0. Clear? And now if you differentiate the both sides, you do get that c2 has to be 0, right? Yes, and if c2 is 0, then of course c1 has to be 0. So c1 and c2 has to be 0. So they are linearly independent. You can argue like that also. It's not a problem. Okay, and so you can do it for any n. So basically 1x, x square, x power n, they are linearly independent. That's going to be the case. Okay, now let's look at another example of a vector valued function, right? So x of t given by e to the power t, clear? And 1 of t and x2 of t given by e to the power 2t and 3 e to the power 2t. Let's just assume that. Okay, so do you think, the question is this, do you think they are linearly dependent or independent? Okay, you see, the thing is, if they are linearly dependent, one vector has to be multiple of another, but here clearly you can see that this does not work. You see, even it may be multiple for one particular value, okay, it may be multiple for one particular t, but for this thing to work here, the difference with the general vectors and this one is, since they should hold for all t, it makes life complicated. So basically c1 times e to the power t plus c2 times e to the power 2t and 3 e to the power 2t equals to, let's say, 0. So basically you do realize this 0 is in R2. Okay, it's a 0 of R2, not like 0, 0, right? Okay, so this will actually imply two things, right? c1 e to the power t plus c2 e to the power 2t has to be 0. This is in R, this is 0. So this is in R2. So let me put it this way. This is 0. And of course, again, by equating, you have c1 e to the power t plus 3c2 e to the power 2t. This has to be 0. Clear? Now you do realize that if both the cases has to hold, then c1 has to be equals to c2 has to be equals to 0. So therefore x1 and x2 are linearly dependent, right? So please make sure that what I'm trying to say is, you understand that this relation must hold for all t in wherever the interval is, right? So that has to be true. Okay, so from now on, I will always write it as LD or LI, meaning linearly dependent or linearly independent, right? Okay, now we define something called definition. We define a new sort of function which we are going to call a Wronskian function, right? We are going to define, so given, let's say, given n vector valued function, okay, and how is it given? Let's say it is given by x1 of t, xn of t, clear? Okay, and then you define, so given all this function, okay, the determinant w, I will write it like this, determinant of x1, x2, xn. Yeah, see, this of course depends on t, right? This, so we can also write it like w of t, right? So given those functions, w is a new function which depends on all these functions, okay, and that will be nothing but the determinant of this. So essentially, you see, x1 is a vector, x1 or xi, right? This at any point t is nothing but an element of Rn, right? So xi of t, if you think about it, it should look like the component. So basically, let's say xi, the first component, xi, the nth component, right? It should look like this. So we will write all these things together and then we just look at the determinant. So basically, it will look like this: x11 of t, x12 of t, x1n of t. Okay, and this goes on, and then this is again xn1 of t and xnn of t. Okay, so you just put you see, x1 you put it in the first column, x2 you put it in the second column, like this. So put one in the column, but it doesn't really matter. You can do it the other way also. But anyways, so because since we are dealing with determinant, but so essentially this is called the Wronskian. So this is called the Wronskian. Okay, Wronskian. So what is the Wronskian? Basically, it's a function. Please understand this. This is a function. What sort of function is it? Wronskian is a function. So Wronskian is a function from t. See, this depends on t. So basically, it is taking values, given the n functions, it is taking values in whatever interval t is defined. So let's just assume that t is defined in I. And what is the end product? W of t is going to a determinant. So basically, R. It's a real valued function. Clear? And now let me ask you this question. See, you do realize that this is basically, I mean, since this is a determinant, this Wronskian is going to be a continuous function. Okay, that is very easy to see, right? It's just a determinant function. Okay. So that's a continuous function, right? Now, the important thing which we need to understand is this theorem. And this is a very, very important theorem. So what does this theorem say? So please remember this theorem. We are going to use this theorem a lot. So if the Wronskian, okay, and for now I will just always write Wronskian as W of t, without any exception. So this is Wronskian of n vector valued functions. Okay, what are the functions? x1 of t, xn of t, okay, is different from 0. Clear? So basically what I'm trying to say is the determinant is non-zero for at least one point in the interval. Okay, for at least one point on the interval, one point of the interval, okay, I, let's say, then these functions are linearly independent in I. Okay, linearly independent in I. Clear? So basically what I am trying to say is this. See, the Wronskian doesn't have to be, it's like not like it has to be 0 everywhere, or non-zero for all t, just for one t, if you can show that is different from 0. Okay, so basically it is non-zero for at least one t in I, then you have that the functions are linearly independent. So how do you prove something like this? Let's look at the proof of this. So you see, first of all, let's assume that since I am saying that we have to prove they are linearly independent. So if they are not linearly independent, it can be linearly dependent, right? So let x1 of t, x2 of t, xn of t, let's say, be linearly dependent in I. Clear? So if that is the case, then there exists, so that implies that there exists constants, okay, constant or maybe yes, constants, we don't know, C1, C2, Cn, not all 0, at least one of them is non-zero, such that you see summation, right, I equals to 1 to n Ci, okay, xi of t, this is 0, right, in I, whatever the interval is, right? That's the definition. That's the definition of linearly independent. Okay. Now, what does this say? See, if you break it up, so if you break it up, let's do it here. Just a little remark kind of thing, or maybe a little something to note. You see, for 2, n equals to 2, let's just see n equals to 3. What does it mean? It means C1 times x11 of t, x12 of t, plus C2 times x21 of t, x22 of t is nothing but 0, 0. Right? So what does that give you? That gives me that the homogeneous system of equation, right? So this will imply that the homogeneous system of equation, what are the system of equation? C11 x1 plus C2 x21 is 0, and C11 x12 plus C2 times x22 equals to 0. This system of equation has a non-trivial solution, right? Okay, homogeneous system of equation, summation x I k, okay, k is the component, the kth component, okay, of t Ci, this is 0, I equals to 1 to n. Clear? You understand? I am just writing it in terms of a shorthand notation. So that will imply, you see, C1 x11 plus C2 x21 is 0, and C1 x12 plus C2 x22 is 0. This is what I am just writing. Okay. So this homogeneous system of equation has a non-trivial solution, right? Non-trivial solution. See, at least one of the Ci's are non-zero. So basically it says that this system of equation has at least one non-trivial solution. Okay, right. Now you see, we know that this homogeneous system, okay, this homogeneous system has a non-trivial solution. This we talked about in the first week, right? Okay, so this homogeneous system has a non-trivial solution when, if and only if the Wronskian is 0. Okay. So now that will imply that this should imply both sides, that the Wronskian at the point t has to be 0, right? What is the Wronskian? Wronskian is nothing but x11, x21, x12, x22, right? This should be 0. That's the only way it can happen. See, this is just a ODE, this is just a system of equation, right? For a fixed t, let's say, it's a system of equation. So essentially what is happening is you are basically showing that if the Wronskian is 0, then C1, at least one of the C1 and C2 has to be non-zero. Okay. So this is what I am just saying in cross for a general n. So that will imply that Wronskian of t has to be 0. Okay. But you see it is given that Wronskian of t is different from 0 for at least one point, but this says that Wronskian of 0 t is 0 for all t in I, right? Yeah, but Wronskian of t is not 0 for at least one t in I. So that is given, which will actually give you a contradiction. I hope this is clear. Huh? So again, let me put it like this. Here in this sort of thing, since we are dealing with n cross n systems, okay, things look a little complicated. What you can do is you break it up into 2 cross 2 systems, huh? And you can be rest assured that if it works for 2 cross 2, this sort of thing, at least in these basic levels, whatever theorems are there, if they work for 2 cross 2, it generally speaking, of course, I mean most of the times they work for n cross n. Okay, right. So this is true. So what did we prove? We proved that if you have a Wronskian, so given n vector valued functions, you define a Wronskian. If that is non-zero at least one point, then you are basically dealing with a linearly independent set of functions. Clear? Okay. Now what about the converse? What is the converse? So basically the converse says that if you have a set of vectors x1 of t, vector valued functions, that is xn of t, are linearly independent. Does that imply, okay, that the Wronskian of x1 xn of t is 0 in I? Do you think that is true? Although it may look like it is true, it is actually not true. Okay, so let me give you an example. So basically let x1 of t is nothing but t1 and x2 of t is nothing but t square and t. Clear? Now it is definitely not difficult to see that x1 of t is equals to t times x2 of t, right? And definitely that is not linearly dependent, so hence it is linearly independent. That is trivial. Okay, so it is trivial to check that x1 and x2 are linearly independent. Okay, so that's not a difficult thing. What about the Wronskian? As you can see, the Wronskian of x1 and x2, if you calculate it, it is t1 t square t, so which will be 0 for all t, right? For all t in whatever interval I. So you see that this example shows that this shows that Wronskian non-zero in I is not necessary for linear independence. So now we are going to look at the this converse. When is it valid? So essentially we have this new theorem. So this theorem says that let x1 of t, x2 of t, xn of t, okay, be linearly independent solutions, not anymore any functions, linearly independent solutions, okay, of the differential equation of the differential system, that is of the system x prime t equals to at times x of t, the homogeneous system, that is. So if they are linearly independent solutions of a homogeneous system in I, then you can guarantee that the Wronskian will be non-zero for all x in I. Yes, I hope this is clear. See, what I am trying to say is this: if the Wronskian is 0 is not a necessary condition for linearly independent. So the example which we just saw, we saw that they are linearly independent, but not necessarily the Wronskian is non-zero. So Wronskian can be 0. Yeah. So essentially what they are saying, what this theorem says, that if they are not any function but linearly independent solution of some system, then there is a guarantee that the Wronskian is non-zero. So basically, if you have linearly independent, so as a remark, if one is working with linearly independent solutions, right, of a homogeneous system, then what can you say? System, then Wronskian not 0 will imply that x1, xn, they are linearly independent, okay, and vice versa. So basically Wronskian non-zero means they are linearly independent. If x1, x2, xn's are linearly independent, it means Wronskian non-zero. Okay, so both sides are true. So let's look at how to prove something like this. Okay, so another theorem. Okay, so this theorem. Okay, so the proof. So let x naught is in I, yeah, be such that, so I am looking at a point such that the Wronskian at x naught, okay, or maybe let me put it as t naught, it will be better. T naught, this is non-zero. Oh, sorry, this is 0. So see what I have to prove. I have to prove the Wronskian at, sorry, I should write it as t, because I am writing t everywhere. I should not write it as x. It will be confusing for you guys. Let's do it this way. Okay, so let t naught is in I. So what I need to prove is this. See, if they are linearly independent solutions of some system, not any function but solutions, this is important, solutions, then the Wronskian is not 0. So basically what I am doing is, let's start with the point t naught where the Wronskian is 0. Let's see what happens. Okay, then there exists, if the Wronskian is 0, then there exists C1, C2, Cn, not all 0, such that, okay, the system summation I equals to 1 to n Ci xi of t, yeah, not is 0. Clear? This is okay. See, the thing is, if the Wronskian is 0 at the point t naught, so if you look at this system at the point t naught, so you know this particular thing, this particular system at the point t naught. Okay, so we looked at this thing, right? This system at the point t naught, you see, that will actually guarantee that you will have at least one Ci which is non-zero, such that the system is satisfied, the system works. Okay, since now you see what is happening is this, I will define a new function xt. Now xt is nothing but summation. So basically what I am doing is this. See, I started out with this system, yeah, and since the Wronskian is 0, then we can say that at least one of the Ci's are non-zero, right? I hope this is clear. Let me do it here so that you are not confused. C1 x11, let's say, is the first component of x1 of t naught, plus C2, the first component of x2, 1 2, sorry, one second, I am doing some mistake. C2 x21, x21, sorry, x21, the first component of x2, t naught equals to 0, and again C2 of x21, sorry 1 2, the second component of x1 plus C2 x22, the second component of x2 t naught is 0. See, the thing is, this equation can be written like this, right? x11 at the point t naught, x21 at the point t naught, x12 at the point t naught, and x22 at the point t naught times c1 c2 is 0 0. Now this is a system, right? And this system is basically this one. This is what I wrote, in a compact form, this one. Now see the Wronskian, this is nothing but this quantity is nothing but the Wronskian of x1 x2 at the point t naught. So if this Wronskian is given to be 0, you see at the point t naught it is given to be 0. What does that say? It says that this system, at least one of the, as a non-trivial solution, so at least one of the CIs is non-zero, right? So that is what I wrote here. Now, so you have this set of C1, C2, Cn such that at least one is non-zero, right? So I will use this set of CIs, okay, and I will create a new function x of t which is based on this C1, C2, Cn. So basically it is Cy of Ci xi of t. I will define it like this. Is this clear? This is not any Ci. Please understand, for that t naught I get a set C1, C2, Cn such that at least one of them is non-zero. I will take that set of C1, C2, Cn. I will define a new xt using that. Okay. Now see, this by the superposition principle solves the homogeneous problem, homogeneous system. Homogeneous system, right? Yes, because that is solved for any C1, C2, Cn, and xi is a solution, right? Xi is a solution for all I. So Ci times xi sum is given by, which is we are defining to be x of t. That is also solving the homogeneous system, principle of superposition. So this is principle of superposition. Principle of superposition, right? Okay. Now you see what happens x at the point t naught. What happens to that? That is nothing but summation I equals to 1 to n Ci xi at the point t naught, right? See, and for these Ci's, a summation I equals to 1 to n Ci xi at the point t naught is 0. Okay, so you have x of t satisfying the homogeneous system, so which is given by x prime of t equals to at times x of t. Okay, and x at the point t naught is 0. Okay, so by the existence and uniqueness theorem, Picard basically, okay, we can guarantee we have x of t is identically equals to 0, right, for all t in I. I hope this is clear. Okay, and therefore since x1, x2, xn's are linearly independent, since x1, xn are linearly independent, okay, what happens? What can you say? That each Ci has to be equals to 0. That will imply C1 equals to C2 equals to Cn has to be equals to 0. There is no other option, right? Okay, so this actually is a contradiction, right? Because we just assume that at least one of the Ci's is non-zero, and but we are showing that all has to be 0. So a contradiction. So what happens is, if you have this linearly independent solutions, then Wronskian non-zero implies that they are linearly independent, and if they are linearly independent, it means that the Wronskian is non-zero. Okay, now we will finish this lecture with a very important property. Property is called as the Abel's formula. Okay, it's called Abel's formula, Abel's theorem, or formula, whatever you want to call it. So essentially, I have whatever the statement I gave just before this, that statement I gave using Abel's formula, without mentioning it. So essentially, let me do it this way. Let x1 of t, xn of t, okay, be the solution of the homogeneous problem, solution of x prime equals to at times x, right? And let's say I am assuming there is a point t naught, there is a point t naught in I, clear? Then for any x in t in I, one has Wronskian at any point t will depend on Wronskian at the point t naught times exponential of integral t naught to t trace of at dt. Okay, what is the trace? It's basically the sum of the diagonal elements. Okay, right. Now, how do you show something like this? So essentially, there is this small remark. Before we show this, let's do this small remark. See, if Wronskian at the point t naught is 0, okay, so basically for some point if the Wronskian is 0, since the exponential is never going to be 0, that will imply that the Wronskian is 0 for all points, for all t in I. So that is why I was saying that if they are linearly independent, it will be 0 everywhere, and if it is 0 everywhere, then they are linearly independent. Okay, it doesn't have to be at one point. If it is non-zero at one point, then it will be non-zero everywhere. Okay, right. So how do we prove the Abel's theorem? So let's do that. You see, if you remember, in the first week we talked about the derivative of a determinant function, right? You remember? So you see, Wronskian is nothing but a determinant function. So w prime of t is nothing but sum. You remember that we did it, right? 1 to n. Row wise this thing, the derivative thing. So let's do it. x1 1 of t, n1 of t. Okay, so the first component, the nth component of the first thing, xn of t, and x the first component, the first function x1, the ith component t, derivative of that, x n I of t, derivative of that, right? Yes, so this is from week 1. If you forget it, please look at week 1. We did this. Okay, so once you have this, you see x1 I, okay, prime of t. See, x1, x2, xn of t is nothing but the solutions of that equation, right? So x1 I prime of t is nothing but sum, if you write it properly, it is a ik of t, okay, x jk of t, right? And this is k equals to 1 to n. Clear? See, x1 prime is nothing but that. So basically, if you break it up, okay, x1 prime, x2 prime will be nothing but that matrix times x1. So you can compute that. So essentially, this is what we are going to get. Clear? And now, if you put it in the this above expression, clear? and multiply the first row with AI1. So multiply the first row with AI1, let's say, okay, of t. The second row with AI2, second row with AI2, okay, of t, of course, and you go on doing this, except the ith row, and subtract their sum from the ith row, okay. So except the ith row and subtract their sum from the ith row, okay. Then what happens is you get that w prime of t is nothing but summation I equals to 1 to n aii of t, the Wronskian of t. Clear? This is a equation, you see, this is a basic ODE, very simple first order ODE, right? So that will imply that this is nothing but w prime of t is trace of at times w of t. Now you just integrate it and you get your result. What is the one second, yeah, where is the Abel's theorem? Yeah, you get this result. Once you integrate it, you get this result, okay. I hope this is clear. Again, I am telling you, if you find this complicated, because there are a lot of indices which are involved, what you do is you break it into a 2x2 system, okay, 2x2 system, and then of course you can use induction or that sort of thing. But the thing is, by doing a 2x2 system, you can just figure it out why these sort of indices are working, okay, and it will be much clearer for you. So please check this part. Check this. What do you check? You do this exact same theorem, but do it for 2x2 system. If you want, you can just explicitly write everything, break it down, write everything, and do it, and then it will be very clear to you. So with this, we are going to end this video.